So welcome to this lecture on principal stresses. In the last lecture we have seen if loads are known on a machine component, then from that load we can find out a stress element. That means because of that load at a particular point, what are the different kinds of stresses are acting that we can calculate or we can identify. Now here in this lecture we will try to see that if we know the stress element, that means at a point at different directions, if we know what are the stresses acting, then it is possible to find out a particular orientation where the stresses will be maximum. These maximum stresses are called principal stresses, where there will be no shear stress, only normal stresses are there. Okay, so principal stresses are the maximum normal stresses in such planes where there is no shear stresses at that point. Now, truly speaking, this particular topic is basically on stress transformation, but with an objective. We have started this lecture series where the main objective is to clear our concepts on design, and that's why for the application of the theories of failure on a particular machine component, and the whole objective or the ultimate objective of all this stress transformation finally comes to the finding out the principal stresses. So that is why the sole objective of studying this stress transformation is to find out principal stresses, and that's why we have given the name of the topic as principal stresses. Now here you can see a most general state of stress at a point. Here you can see three-dimensional stresses are acting at a point Q, and around which we have basically considered this orientation of planes, where you can see that sigma x, sigma y, sigma z are the normal stresses, and tau xy, tau yz and tau zx, these are the shearing stresses and their direction. Okay, now if you see, instead of this x, y, z coordinate system, if we change this coordinate system to say x prime, y prime, z prime, a different coordinate system, definitely for the same state of stress at that point Q, we'll get different stress components. That means instead of previously the sigma x, sigma y, sigma z and tau xy, tau yz, tau zx, instead of these six components, now we'll get sigma x prime, sigma y prime, sigma z prime, and tau x prime, tau y prime, and tau zx prime. So only by the orientation of the axis system we'll get different stress components. That means different normal and shear components will get, but remember the state of stress at point Q is same. Only because of the orientation of the axis we are getting different stress components. Now in the stress transformation we'll see that how these components are related to these components. Okay, if you know that what is the orientation change of the axis system. Now let us make it simple and consider a plane stress situation. In a plane stress situation, it is basically there is no sigma z. Let us consider it is, we are considering the plane as xy plane, so there will be no sigma z component, and tau zx and tau zy components are also 0. So out of those six independent components, now there are only sigma x, sigma y and tau xy. These three components are there. Two normal stresses and one shear stress components are there. So this situation is called a plane stress situation, and it is not that plane stress situations are not in practice. This kind of situations is not there. Very much there are many situations that we can consider as a plane stress situation. It is not only for the simplification of the mathematics. Definitely it will help in simplification of mathematics, but there are many practical situations where the plane stress assumptions is good. For example, the plane stress assumptions is true if you consider a very thin plate subjected to forces acting at the mid plane of the plate. But more than that, this is a much more common situation where maybe a complex loading or a combined loading is there on a machine component. Here you can see that torsional load is there because of this force. Maybe bending load is also there. Okay, so because of this complex loading also, at the surface element, if you see, that must be in the plane stress condition, unless otherwise some force is acting exactly at that point. So remember, any machine component, if it is if you consider a point at the surface, that surface point must be at a plane stress condition, unless otherwise at that point you are applying certain external forces. Okay, so this is a very important point, or the practical situations where we can assume plane stress condition even the body is three-dimensional, the loading may be in a different directions. Now plane stress transformation equations. Now here you can see a plane stress situation, that sigma x, sigma y, normal stress is in x and y direction, and tau xy is there, which is acting. Okay, now suppose we want to find out the stress components at a different orientation. That means if you consider that this orientation has been changed by an angle theta, then what is the normal and shear components that we want to find out. That means we want to find out what is sigma x prime, what is tau x y, x prime y prime, or what is sigma y prime if the rotation is by an angle theta. So these prime components are related to this sigma x, sigma y and tau xy components by these stress transformation equations. What is that relation? Here you can see the normal component in the x prime direction will be equal to sigma x, sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau xy sin 2 theta. So all these components are in the xy direction, and with the help of the components in the xy direction, it is possible to find out the normal stress at an angle theta with the x-axis, that is sigma x prime. Similarly, we can also find out tau x prime y prime, that is minus sigma x minus sigma y by 2 sin 2 theta plus tau xy into cos of 2 theta. Okay, so these things can be find out. So this is the stress transformation equations. Only by considering the equilibrium in a particular direction, this can be derived. Now we can also find out sigma y prime. As you can see that sigma x prime and y prime are 90 degree apart. That is why in place of theta, just you put theta plus 90, you will get sigma y prime. So this is what is the expression of sigma y prime. Okay, so what we have done, basically in place of theta, if we put 90 plus theta, you will get this expression, that is corresponding to sigma y prime. So in this way we can transform one stress component to another stress components at different orientation in a plane stress situation, definitely. Here in a graphical representation, you can see the graphical representation came from the fact that if you look very carefully this particular set of equation, and from these two equations it is possible to remove this cos theta and sin theta components, or in other words, you can remove theta. This parameter theta can be removed by simply finding out cos of 2 theta from here and sin of 2 theta from here, and by considering cos square theta plus sin square theta is equal to 1. So using that, it is possible to find out or eliminate theta. If you eliminate theta, then you will find that the equation becomes equation of a circle. That is why the sigma x prime tau x prime y prime will be the coordinate on the circumference of the circle. So that particular circle actually has been drawn here. Here you can see, if you remove theta, you will find that the expression will become sigma x prime minus sigma average whole square plus tau x prime y prime square is equal to r square, where sigma average is this quantity and r is this quantity. If you simply eliminate cos 2 theta and sin 2 theta from those two equations in the last slide, you will find this expression. And clearly this expression is an expression of a circle where sigma average is the center, sigma average comma 0 is the center, and r is the radius of the circle. So if you draw that circle, considering sigma average comma 0 as the center and r as this quantity as the radius, you will get this circle. This particular circle is also called the Mohr circle, and here you can see that a particular point on this circle indicates what? A particular point on this circle indicates a sigma x prime and tau x prime combination. Is abscissa indicates sigma x prime and ordinate is the tau x prime y prime. So the coordinate of this point basically, or any point on the circumference, indicate the normal and the shear component at different orientation. So that you can see that as you change the value of theta, then definitely this normal and the shear components will change, and if you just plot all these points and if you join them, you will get this locus as a circle. So principal stresses are what? Principal stresses are the maximum normal stresses that occur, maximum or minimum normal stress that occur in the planes where there is no shear stress. If these are the points on the circumference indicates the normal and the shear component of different orientation, that means a different theta, then you can see that at point A, what is the normal component? The normal component is its abscissa, that means this length from here to here, which is the sigma max. And what is the shear component? The ordinate, that is 0 at point. So at point A indicates definitely a particular orientation where you can see the normal stress is maximum and the shear stress is 0. On the other hand, you see the point B where again the shear stress is 0 because it is on the ordinate is 0, and you can see that normal stress is minimum. So A and B, these are the points where the normal stresses are maximum and minimum, and the most importantly the shear stresses are 0. So A and B indicates two particular plane such that at that plane shear stresses are 0 and the corresponding normal stresses are maximum and minimum, and these normal stresses are called principal stresses. Okay, so these principal stresses can be easily find out from this expression, because you can see, if you know, if you want to find out the abscissa of A, just simply add this position of the center plus the radius. So position of the center is the C average and plus the radius you know this one, so this plus this, and to find out point P, that is position of C minus radius, so you will get B. So sigma x plus sigma y by 2, which is the sigma average, and if you plus it, you will get the sigma max. If you minus this radius, you will get the sigma mean. Okay, so these are the principal stresses that we can find out, and you can also find out the angular position with the x-axis. Okay, x-axis means here this is not the x-axis. Okay, x-axis is what you have seen in the last slide. Here you can see this is what is the x-axis. Now at which theta this normal stress is maximum or the normal stress is minimum, that we want to know with respect to this x-axis. So this theta we want to find out. So that theta we can easily find out by considering the maximum with respect to theta. If you differentiate and find out the maximum, you will get this expression. So tan of 2 theta of P is equal to 2 tau xy by sigma x minus sigma y. Okay, so this is the expression by which it is possible to find out the orientation of the principal plane with respect to the x-axis. So these two principal planes, one is A, another one is B, and they are definitely separated in actual plane by 90 degree. In Mohr circle, you can see they are separated by 180 degree, but in actual plane they are separated by 90 degree. So here you can see, if this is the x-axis, then theta p, if you find out it is some positive value, then you see this is the plane where the sigma max will occur, and you can see there is no shear in that plane, and sigma mean will occur at the y prime axis, and that is at a 90 degree from the sigma max. Okay, and this is what is theta p, and theta p may have two values. From tan of 2 theta p is equal to this, so you can find out 2 theta p values of this. So those 2 theta p value corresponding to sigma max and sigma mean. That means corresponding to two principal stresses, you will get 2 theta p values. Clear? Now we can also find out the maximum shear stress, and that maximum shear stress for sigma x prime is equal to sigma average. Here you can see, if you see at the diagram, the in plane maximum shear stress occurring at which point? You can see that is occurring at this point, because this is the ordinate of any point indicates the shear stress, and at which ordinate it is maximum? At the point D, because at that point you can see this is what is the value of tau, and that is maximum. So this is nothing but what? The radius of the circle. So radius of the circle is nothing but the maximum shear stress value, and when at that plane maximum shear occur, what is the value of the normal stress? Normal stress is corresponding abscissa. So this abscissa is what? This abscissa is sigma average. So when the shear stress is maximum, at that point the sigma average is the normal stress value. Okay, so that is why it has been shown that at that point sigma x prime is the sigma average, and there the shear stress is maximum. You can also find out the plane where the shear stress will be maximum. That is by this formula, tan of 2 theta s is equal to minus of sigma x minus sigma y by 2 tau xy. Note, defines two angles separated by 90 degree offset, that means this point and this point. Okay, and if you compare with the theta p where the normal stress is maximum, normal stress is maximum means the principal plane. The principal plane and the plane of maximum shear stress, they are separated by 45 degree. Okay, so in this way we can find out the maximum normal stress and minimum normal stress, which are called the principal stresses. We can find out their planes, principal planes. We can find out the maximum shear stress, and when maximum shear stress occurs at that plane, what is the normal stress that we can find out, and also we can find out the plane where the maximum shear stress occurs. That means its orientation with respect to x-axis. Now let us take one example and try to find out the principal stresses. Suppose because of certain loading, this is the stress components. So definitely it is a plane stress condition. You can see here, you can see 50 megapascal is the normal stress in the x direction, and 10 megapascal is the compressive normal stress, right, in the y direction, and 40 megapascal is basically the shear. So the problem is you have to find out the principal planes, principal stresses, and the maximum shearing stress and the corresponding normal stress. Okay, so things are very simple. Just use the formula where the principal plane occurs. You know tan of 2 theta p is equal to 2 tau xy by sigma x minus sigma y, and you know tau xy is what? Tau xy is 40 megapascal. You know sigma x and sigma y. What is sigma x? 50. What is sigma y? Sigma y is not plus 10, sigma y is minus 10, because 10 sign is considered to be positive. Okay, and what is tau xy? Tau xy is 40, because at this plane you can see this is the direction which is considered for the positive for the shear stress. Okay, so this is considered to be positive, so tau xy is plus 40, that is considered. Regarding the sign convention of the shear stress, you just try to remember this thing, then it will be helpful. You see that there are two suffixes x and y, right? The first one indicates the direction of plane, and second one, that is y, indicates the direction of the shear stress. So tau xy, so this x is the direction of the plane, right, and y is the direction of the shear. Here you can see that x is the positive direction of the cross section, the positive direction of the plane. That means if this is the plane, outward normal is considered to be positive, and that is the positive x direction. And y, you can see this is what is the positive y direction. So this is what is the positive direction of the shear. So that is why if the shear is in this direction, that is taken to be positive. But suppose the shear at this plane was in the downward direction, then it would be negative. Why? Because in that case the plane direction is x, that is in the positive x direction. So direction of shear stress should be in the positive y direction, should not be in the negative y direction, and that is why that would be negative. But here in this case, you see this is also positive, but it is pointing downward. Why? Because here the direction of the plane is what? You see the direction of this plane is negative x-axis. If the direction of the plane is negative x-axis, then definitely the second one, the direction of the shear also should be in the negative direction. Then it is considered to be positive. That is why this one is positive. So both this one and this one are positive. So this is what is the sign convention of the shear or the sign convention of the stress tensor is considered. Now principal stress, how we can find out? Simply sigma average plus minus the radius that you know. So you know all these components, so you can easily find out the principal stresses. Third one, find out the maximum shearing stress. Maximum shearing stress, you know what will be the in plane maximum shear. In plane maximum shear will be the radius value, and that you can find out. And what will be the corresponding normal stress, that you know the average value. Okay, so here in this particular case, you see tau xy is plus 40 megapascal, sigma x is plus 50, but sigma y is minus 10 megapascal. Now use these values and find out each of the component. Here you see tan of 2 theta p is 1.333. So from that you can find out theta p having two values, 26.6 and 116.6. So these are the two planes where you will get the shear stress is 0 and principal stresses will be maximum and minimum. So you see that sigma max and sigma mean will be corresponding to these values. One is 70 megapascal, another one is minus 30 megapascal. You see on the plane, so here you can see 26.6. So with respect to x-axis, if you move by 26.6 degree in the anti-clockwise direction, then you will get this principal plane, one principal plane. And if you move by 116, you will get another principal plane. So here it is 70 megapascal, you see, and here it is 30 megapascal, but compressive in nature. That is why negative. So similarly, you can find out the maximum shear stress by using this formula, and maximum shearing stress corresponding plane, that you can find out by theta p, that means the principal plane, minus 45 degree. Okay, because you know that plane of maximum shear and the principal plane are 45 degree apart. So one will be theta p minus 45 degree, another will be theta p plus 45 degree. So in this way you can find out that. Now coming to another example, here you can see, suppose there is a member that you can see where the load P is applying at this location. All the dimensions are given, and the problem is if you consider that point H at this surface in a which is parallel to xy, say at this point, the problem is you find out the normal and the shearing stresses on the element, and also find out the principal plane and the principal stresses at point H. So here the problem started from the loading that we have discussed in the last class. So from the loading, first we have to calculate the stress element. From the stress element we have to calculate the principal stresses. Okay, so let us see how we can do that. So first tell me what kind of loading will come. Because of this, definitely there will be a twisting about the y-axis, so a torsion will come, and because of pure torsion, shear will come. Now not only that, because of this loading there will be chance of bending, right? So because of bending, normal stresses will also come at this edge. Since it is at the outer surface, because of bending the shear will be 0, only the normal stress will be there. So what are the stresses that will act at the outer surface point H? One is shear stress because of torsion, another one is the normal stress because of bending. So we'll find out this, and finally we'll find out the principal stresses. So if you just cut it at that position, and here you can see what is H. So you can see that there will be a torsion corresponding to this value. That is very simple, because the P multiplied by this length 18, so that will be the torsional value. Okay, and you can also find out the bending, and bending will be what? Simply this P multiplied by this length, that means 10 inch. So P multiplied by 10 inch will be the bending. So in this way you can find out the torsional load, you can find out the bending moment. Okay, and the shear, direct shear will be because of bending there will be no shear, because it is at the outer surface. Okay, so you first find out what is the P, what is the torque, that you can see, what is the bending moment, that you can easily find out. It is very important, their directions. So once you know, you can find out what is sigma y. Sigma y is the normal stress that will act on that element. That will be according to the formula M into y max into I. That y max is basically called the C. That means with respect to this cross section, you have to consider what is the value of the C. That is nothing but the diameter, radius. Okay, so radius has been considered here in place of C. M is known, and I is, for the circular segment, it is pi by 64 d to the power 4. Okay, so that value has been considered. In terms of radius, it has been written, that is why 1/4 pi into r to the power 4. It has been written. Similarly, you can find out shear stress from the torsional formula, that T into radius divided by the polar moment of inertia, and polar moment of inertia half of the area moment of inertia, that is, you can see, half of pi into radius to the power 4, and torsion is 2.7 and 0.6 is what is the radius. So in this way you can find out the normal stress because of bending and the shear stress because of torsion. Okay, so finally, so sigma x is coming 0, and the sigma y, it is plus of this, and tau xy is 7.96. Once you know the stress element and different stresses that is acting because of this combined loading given, you can draw the stress element. So this is what is the stress element. Now you know all these values of sigma x, sigma y, and tau xy, because this is a plane stress situation acting at the outer surface point H, right? So now for that you have to find out the principal stress. Okay, so the next part you have to do that, you find out the principal planes first using this formula. You know tan 2 theta p is 2 tau xy by sigma x minus sigma y. You know sigma x is 0, sigma y is there, and tau xy is there. So using that you find out theta p. You will get two values of theta p. Now you find out sigma max and min using this formula, and you get these values of sigma max and sigma min. So you can see that sigma max and sigma min are these two at different orientations. One is at minus 30.5 from the x-axis, where it will be the sigma mean, and another one is 59.5, where it will be the sigma max. Now the same thing can also be done with the help of Mohr circle, because that is also a method by which graphically we can visualize easily these different stresses and the principal stresses. Now here what is done, the one thing you have to understand first, that this axis is basically the normal stress axis, sigma axis, and this vertical axis is basically the shear stress axis. The one thing that you have to remember is what you have to plot is, if you consider this tau to be positive, okay, in the sign convention that we have mentioned, then you have to plot sigma x comma minus tau xy here, and sigma y comma plus tau xy here. Or in other words, what you can do instead of that, you just consider this shear stress positive as the clockwise. So positive shear stress you just consider clockwise, and negative shear stress you just consider anti-clockwise. So if you consider anti-clockwise, then you can plot that particular normal and shear stress in this coordinate axis. Okay, so I have told you two methods. Once again I am repeating regarding the shear stress sign convention of plotting in the Mohr circle. The first method is you just consider this shear stress axis as positive, whatever we have mentioned earlier. That means the sign convention of shear stress, that means tau is positive according to the sign convention. In a very simple words, if we want to see, just see this particular example once again, that this tau xy is positive or negative. This is positive because this is the positive x-axis, and that is why the shear stress direction should be in the positive y direction. Okay, so this is positive. Or in other words, you can think in that way also, that if you consider any inner point within that element and this particular force is trying to rotate in which direction, if it is trying to rotate in the anti-clockwise direction with respect to some inner point, then it is positive. But it is always remember that the first one is the ultimate sign convention, that first see what is the direction of that plane. If that direction of the plane is matching with positive x direction, then the shear stress direction should be positive y. If that direction of the plane is matching with negative x, then the direction of shear stress should be in the negative direction, then it will be considered to be positive. So this is what is the sign convention. Or in other words, with respect to some inner point, if the force is trying to rotate the element in the anti-clockwise direction, then it is considered to be positive. This is what is the sign convention of the shear stress. So in that sign convention, this particular shear stress is positive and this particular shear stress is negative. Clear? Because with respect to this inner point, this shear stress is trying to rotate in the clockwise direction, that is why negative. Again, with our sign convention, this tau yx, if you see that this tau yx, this is what is the sign convention that we have just mentioned. Now you go to this example and you see that which one, suppose sigma, this tau is then anti-clockwise positive. Suppose you are plotting in a sign convention that we have mentioned, that means if this is anti-clockwise then it is positive, then you have to plot one point, that is sigma x comma minus tau xy, another point as sigma y comma plus tau xy. Then you have to join these 2 points. It will cut a point on this axis, that will be the center. You take that radius and draw the circle. Okay, or what you do, you keep your sign convention, that is anti-clockwise positive is okay, but in that case what you have to do, you have to consider this positive tau as the clockwise, and anti-clockwise you have to consider to be positive in this direction, and then you can plot sigma x comma tau xy and sigma y comma minus tau xy, no problem. But remember that the positive tau will be in the downward direction. Then again you will find that you are basically getting the same point here and here. So in the two way we can draw the Mohr circle. So here what has been done, you can understand that it is considered that tau anti-clockwise is positive, which has been shown upward. So in this diagram what has been shown, that anti-clockwise is positive, okay, and clockwise is negative. Now if anti-clockwise is positive, then what you have to plot is that sigma x comma minus tau xy, that you have to plot, okay, and here you have to plot sigma y comma tau xy. Suppose this is your element where this is your tau xy and this is your sigma x. This is your sigma x, this is your tau xy. Suppose this value is 100 and this value is say 50. So what you have to plot is that anti-clockwise positive is the upward direction, and what you have to plot is 100 comma minus 50. That you have to plot. You have to plot this one as a point. Here you see sigma x comma minus tau xy. Okay, and another one that you will have to plot is sigma y comma plus tau xy. So sigma y comma plus tau xy. That means if that is 50, so maybe sigma y is say 70. So what you are plotting is 70 comma 50 is this point. Okay, so you have to plot these 2 points, then you have to join. You will get the center, take this radius, draw the circle. This is the way by which you draw the Mohr circle. Once the Mohr circle has been drawn, you can easily find out the principal planes. So this length will be the sigma max from here, and this length will be the sigma mean. That's all. You can easily find out the principal stresses. And what is the principal plane from the x-axis? That also you can find out, because this is what is the x plane. This is what is the x plane. What is the state of stress at the x plane? That is sigma x and tau xy. That means this point. And what is the principal plane? This point. So what is the angle? So this is the angle. So remember, find out that angle and make it half. Remember, everything in the Mohr circle is twice of the actual element. Okay, so this will be the 2 theta p. So the actual plane, if you see, this will be probably the theta p. That will be half of this angle, where you will find the principal stress. Okay, so in this way it is possible to find out the maximum and minimum stresses, that means the principal stresses. It is possible to find out the position, it is possible to find out the orientation of the principal planes. So now here you can see another example. Suppose you know a particular plane, say this is the position x-axis, sigma x and tau xy. So sigma x tau xy. So what we have to plot? We have to plot sigma x comma minus tau x. That has been plotted. This is sigma y comma plus tau xy. That has been plotted. So this is point corresponding to x-axis. This point corresponding to y-axis. Now suppose you want to know at some point which is at an angle, say any arbitrary angle, say theta, from the x-axis. I want to know what is the stress, normal stress and shear stress component. Okay, so what we'll do, you simply rotate by an angle 2 theta in the Mohr circle. So in that direction, suppose here we want to know a plane which is say theta in the clockwise direction. So what you have to do, you have to move 2 theta in the clockwise direction. Then you will get this point, and in the opposite to the diameter you will get this point. So from the abscissa and ordinate of this point, you will get the normal and shear component. From the abscissa and the ordinate of this point, you will get the normal and shear component of these 2 perpendicular planes. Okay, so in this way it is possible to find out any stress transformation without using stress transformation equations. From graphically it is possible to find out the normal and shear component at different orientation. So here you can see the Mohr circle of a centric axial loading. That, if you remember, the truss member where axial loading is acting, and because of that, if you see a stress element, the stress element will have only the axial stress, normal stress. There will be no shear, there will be no y component, right? So in that case, sigma x is simply p by a, uniform shear, uniform normal stress, and sigma y tau xy, these are 0. So now if you draw the Mohr circle of this element, you will see this will be the Mohr circle, and this Mohr circle will be tangent to the vertical axis, right? So what are the principal stresses? Basically this is the principal stress. One principal stress is this sigma x comma 0, another principal stress is 0 comma 0. So these are the principal planes basically. Okay, so you can also find out that for this kind of element where the shear will be maximum, yes, definitely you can find out the shear will be maximum at this point. And what is that magnitude? You see the maximum value of shear is the radius. And what is the radius? That is, this is sigma x, right? From here to here this is sigma x, so this will be sigma x by 2, and sigma x you know p by a, so maximum shear is what? P by 2a. And at which angle it will occur? From the x-axis you see this D, this particular plane where maximum shear will occur is at an angle 90 degree. So in actual plane it will be what? It will be at an angle 45 degree. You know the half of the angle will be in the actual element. Okay, so maximum shear will occur at an angle 45 degree. Now see in case of torsional loading. Suppose this is a member and it is under torsional loading. What you know? That only pure shear will act, right? This kind of shear. There will be no normal stresses. So if you draw the Mohr circle or corresponding to that, you will find the Mohr circle will be like this. Because one sigma x is 0, sigma y is 0, and tau xy is what? T into C divided by J. Now you just plot sigma x and minus tau xy. You plot sigma y and plus tau xy. You will get these 2 points, and now you draw the Mohr circle. You see where the principal stresses are occurs. Principal stress occurs as point A and B. So how much at which orientation from the x-axis? You see at an angle 90 degree, because this is what is the x-axis. So from x-axis it is at an angle 90 degree in the Mohr circle. So in actual plane it will be 45 degree. So at an angle 45 degree from the Mohr circle, it will be the normal stress, that is maximum. Okay, that means principal stresses. Okay, similarly we can find out in the other perpendicular to that, that will be the compressive stress of the same magnitude. Okay, that is acting. So in this way we can find out the principal stresses for this kind of torsional loading or axial loading or any other kind of loading if we know the stresses that is acting on an element. Now this is the same example. Suppose the stress element is like this, then using the Mohr circle you find out the principal stresses, principal planes and maximum shear stress. So this is very simple. You know that what you have to plot, it is 50, that is the normal stress sigma x, and this is 40 tau xy. So what you have to plot? 50 comma minus 40, right? So 50 comma minus 40, that is corresponding to, that is sigma x comma minus tau xy. So that has been plotted here. Okay, and corresponding to y, what you have to plot? It is minus 10 comma plus 40. Okay, so minus 10 comma plus 40, that has been plotted. So if you join it, you will find the center, and once you know the center, you can find out this distance. This is what is the average, and you can also know the radius. Okay, so you can easily find out this point and this point. So these are nothing but the principal planes. You can also find out what is the angle, that means the principal plane's orientation with respect to x-axis. So everything you can find out from this diagram. And finally you have to interpret whatever results you are getting. Remember, minus some angle or plus some angle or minus some stress value, these are not important. Important is what is the interpretation of this negative sign, what is the importance of this positive sign, that you have to show in proper physical element. Okay, then it will be of some meaning. So in this way it is possible to find out everything, like the position of the maximum shear stress and what is the magnitude of the maximum shear stress, or what will be the value of the normal stress where the shear stress is maximum. So anything you can find out. Okay. So here is another example where the similar things you have to find out. Okay, here you see what is sigma x. Sigma x is 100. First identify that whether you can understand looking at the figure whether which one is positive or negative. What is sigma y? You see sigma y is also positive, that is 60. I am not writing the unit. And what about the tau xy? You see our sign convention, according to our sign convention we did some internal point. If it is anti-clockwise then positive, so it is negative, right? So minus 48. So once you identify this, then in the Mohr circle what you have to plot? In the Mohr circle, remember, you have to plot sigma x minus tau xy. And what is the other point that you have to plot? Sigma y comma plus tau xy. And remember about the axis that this is tau, what is considered to be anti-clockwise positive. Okay, that means the proper positive or negative sign convention. So counterclockwise is positive, that is what is the sign convention of the tau that we are plotting here, and here it is sigma. So this is the thing that you have to remember. So first you have to plot is what? 100 comma plus 48, because this is already minus 48, so minus or minus 48 it becomes plus 48. So 100 comma plus 48, something here. And what is sigma y comma tau xy? That is 60 comma minus 48, so maybe 60 comma minus 48, something here. So then this is basically x and this is corresponding to y. So now you join these two, you will get the center and you know the radius, so you can draw the Mohr circle. So in this way we can find out now principal stress. Okay, this will be sigma max from here to here, this distance, from this distance it will be sigma mean, right? This angle you can easily measure, and that angle divided by 2 will be the theta p. Okay, so in this way we can also find out everything. And if the problem is the stress component exerted on element obtained by rotating the given element counterclockwise through 30 degree. So counterclockwise, if you rotate by 30 degree, then what will be the stress component? So counterclockwise you rotate by 60 degree. So just a double of this. Okay, so you rotate by 60 degree, then you come to this position, right? So this will be your x prime and y prime. That's all. This angle is 60 degree. Just a double of this. So this abscissa and ordinate will give you its normal and shear component. Similarly, this abscissa and this ordinate will give you its normal and shear components. Problem is over. Okay, so in this way you can solve with the help of Mohr circle also the similar things. So you can see in this way we can calculate quantity. The same thing has been done. Now the general state of stress. Till now we have discussed about the plane stress condition, but the situations can be more general. That means all components, all 6 components are present. In that case, suppose all these components are present, normal components and the shear components. In that case, what you can do, if you want to find out a particular orientations, let us consider this is one particular orientation. ABC is the plane, any orientation plane, and it's this direction of this plane is normal to that plane. Suppose that normal direction is represented by n. This is what is the direction, and this particular direction, let us consider its direction cosines are lambda x, lambda y and lambda z, qn. This is what is the direction cosine of that arbitrary oriented plane. Okay, so it is possible to find out the normal stress that is acting in that direction in terms of the components sigma x, sigma y, sigma z, and this shear components. Okay, and that can be done simply by considering the equilibrium in that direction, and if you do that, you will get that the normal component in that direction, sigma n, will be equal to sigma x lambda x square, sigma y lambda y square, sigma z lambda z square, plus 2 tau xy lambda x lambda y, 2 tau yz lambda y lambda z, plus 2 tau zx lambda z lambda x. So this is what is the expression of the normal stress in that direction, okay, which is arbitrarily oriented such that its direction cosines are lambda x, lambda y, lambda z, and this has been represented in terms of sigma x, sigma y, sigma z, and shear components. So from this expression, it is possible to find out a particular orientation of the plane such that these shear components will become 0. So what will be that orientation where there will be no shear component? So that we can always find out, and we already know that particular orientation is called the principal plane, where there will be no shear components. So if you do that, then we will get the principal stresses. So sigma n, it is possible to express in terms of sigma a, sigma b, and sigma c only, and there will be no shear component. Okay, so these particular planes where there is no shear components present are called the principal planes, and the corresponding normal stresses are called the principal stresses. So here you can see this is the XYZ orientation, and ABC orientation. If you see carefully, A, B, and C, these are the principal stress, and these are the principal planes directions A, B, and C. So along these directions there is no shear component, but you can see in the XYZ direction there is normal shear, all these components are present. But remember, in ABC direction there is no shear components present, only normal components are present. So it is always possible to find out these principal planes and their principal stresses for any general state of strain. So now suppose you know these particular directions. Suppose you know the direction of principal planes A, B, C. Now with respect to C, if you rotate this A and B, that means with respect to C, if you rotate the element, then at different orientation in the AB plane you will get the different stress components, and those stress components can be plotted on the circumference of this Mohr circle. Here you can see that point C, point B, and point A are the principal stresses, okay, in the A, B, and C direction. So this is basically sigma C, this is basically sigma B, and this is sigma A. So first these principal planes are plotted. Then with respect to C axis, if you rotate, then what will happen, that you will find the different orientation, and at different orientation normal and shear component will come in the AB plane, and what you will get, that these values of normal and shear component can be plotted on the circumference of this circle. So considering AB as the diameter, if you draw a Mohr circle, then on that Mohr circle you will get the different points which are basically representing the normal and shear component if that particular element is rotated with respect to C axis. Remember, C axis representing the one principal plane. Okay. Similarly, if you rotate with respect to B axis, which is a principal plane in the CA plane, then again you will get the different components normal and shear, and those will be on this circle. So now you are rotating with respect to B, which is the principal plane, and these are the different points. You will get this Mohr circle. And if you rotate with respect to A axis in the BC plane at different points, you will get these normal and shear components. So here you can see the three Mohr circles, each are corresponding to rotation of the element with respect to one of the principal axis, right? And if you arbitrarily rotate, not with respect to any principal axis, then you will get the other points, which will be maybe that some intermediate point shown in this shaded area. Okay, that will be in that region. But we are mainly interested in these three Mohr circles, and from these three Mohr circles it is clear that the maximum stress will occur at point A. This is the maximum principal stress, then, and this one is the minimum principal stress. And what is the maximum shear? The maximum shear will occur corresponding to this one. Okay, so the radius of the largest Mohr circle. Okay, so how can we find out that? Simply, if you find out sigma A, sigma B and sigma C, and if these three normal stresses, three principal stresses are such that sigma A is the largest and sigma C is the smallest, then sigma A minus sigma C, this is what is the diameter of the largest Mohr circle, that divided by 2 is nothing but the maximum shear. So that is why tau max is equal to half of sigma max minus sigma mean. Okay, so in this way it is also possible to find out the maximum shear. Okay, now we are taking two special cases, that if points A and B are on the opposite side of the origin, depending upon their normal or their compressive or tensile, it is possible they are on the opposite sides. A and B are on the opposite sides. Okay, for this case it is clear that the corresponding principal stresses are maximum and minimum normal stresses for the element. So you can find out that maximum normal stress will be this one, and minimum normal stress will be this one, and the maximum shear stress for the element is equal to the in-plane shear stress, because for the AB, if AB is the element, then you can see the maximum shear stress will be of that element. Okay, because this is what is the maximum. But if the situation is such, and this is what you know, that the maximum shear stress is 45 degree to the principal plane, that we have seen earlier also. But if the principal planes are such that you see both are on the same side, both A and B are on the same side of this axis, in that case you see the maximum shear stress is not this one, but the maximum shear stress is what? The maximum shear stress is this maximum principal stress divided by 2. That means we are talking about a plane stress situation. Basically we are talking about a plane stress situation. Suppose this is the elements that we have seen till now. Suppose the plane stress situation. Okay, so for this plane stress situation, what are the principal stresses? It is possible to find out the principal stresses at a particular orientation, but perpendicular to that plane, what is the normal and shear? Since the shear is 0, so perpendicular to the plane is normal stress is 0, and that is, remember, the one of the principal stress. Okay, so now with respect to that stress, basically you are rotating in that plane. So that is why this what you are getting is basically corresponding to that 0. Okay, so if you consider with respect to that, then you will get this particular Mohr circle, and there maybe you will get this particular thing. That means the maximum shear, in-plane shear, may be this one, but this is not the maximum shear within the whole element, because if you rotate with respect to other principal axis, maybe other principal axis, then you will find maybe out of plane shear you will get here it is maximum. So what you have to see, that you have to first find out what are the values of sigma 1, sigma 2 and sigma 3, and then you order them, that which one is more, which one is less. If the situation is that sigma 1 is more than sigma 2 and is more than sigma 3, then remember maximum shear stress will be sigma 1 minus sigma 3 divided by 2. So this is what you have to remember. For a plane stress situation, suppose for a plane stress situation, sigma A and sigma B are the principal stresses. Sigma A and sigma B are the principal stresses, and suppose sigma A is greater than sigma B. We are talking about plane stress situation. Plane stress situation means perpendicular to that plane there is no stress present. That means plane stress situation. Now in this plane stress situation, what is sigma 1, what is sigma 2 and what is sigma 3? First try to understand the principal stresses in general, even if it is for a plane stress situation. Remember your sigma 1, since that is more than a sigma B, and assume that both are greater than 0. If this is the situation, suppose both are positive, that is the case that we are considering here. Both sigma A and sigma B are more than 0. So in that case, what is sigma 1? Sigma 1 is the largest one among the three principal stresses, right? So sigma 1 is sigma A. What is sigma 2? Sigma 2 is sigma B. And what is sigma 3? Sigma 3 is 0. So what will be the maximum shear? The maximum shear will be sigma A minus 0 divided by 2. That means sigma A divided by 2. So tau max will become sigma A divided by 2. Okay. So here in this example also, here you can see this is an example where sigma A is greater than 0 but sigma B is less than 0, right? But this is again a plane stress situation. Remember, this is again a plane stress situation. So first we have to find out what is sigma 1, what is sigma 2 and what is sigma 3. Now sigma 1, you see which is the largest one, that is sigma A. And what is sigma 2? In that order, sigma 2 is 0. And what is sigma 3? This is the smallest one. So that is sigma B. Okay. So in this way, we can find out sigma 1, sigma 2 and sigma 3. Then what will be the maximum shear? You know that maximum shear is sigma 1 minus sigma 3 divided by 2. So what is sigma 1? That is sigma A. What is sigma 3? That is sigma B. That divided by 2. So that you can see sigma A minus sigma B divided by 2. And that is why in this case you will find that in plane shear is what is the maximum, because maximum shear stress occurs in that plane, in that AB plane, right? But in this case it is not in that plane, it will be out of plane. Okay, but this is what is the basic idea, that how we can find out the maximum shear stress in case of plane shear stress. In case of plane stress element, how can we find out the maximum shear stress? So you have understood how can we do it, and here also you see the maximum shearing stress at 45 degree to the plane of the stress. Okay, plane of the principal stress. In the next lecture we are going to discuss on the strength of material. Okay, then we'll see that how to use the strength of material concept and the principal stresses, and using that we'll see how to design a particular machine component using the different theories of failure.